Okay, so considering the homework, sorry I put it a bit late. I extended it to tomorrow 11:59. There are two small things. So for 4.4, the hint only applies for the well-defined part. Now you can definitely do something to the same hint to show it's injective, right? But anyways, and for 4.8 there is a small typo. It's use parts 5 and 7. So part 5 I think show that the equivalence class of x has the same size as the index of C of x. And part 7 is that show that x is equal to its own equivalence class if and only if x belongs to ZG. And for 4.9, for the last question, it's not an application of just Lagrange. Okay? Yeah?
Yeah, it says it has the cardinality of p to the k.
Yeah, exactly.
Is p prime or just
p is a prime? No, I said p is a prime. I think I said p is a prime. And when I say that ZG has cardinality p to the q, say, for some q in n, this is not just an application of Lagrange. Okay? You need Lagrange, but you need something else as well. Okay? Lagrange tells you that ZG has order p to the q for some q greater or equal to 0, right? For some integer q greater or equal to 0. I need you to eliminate the fact that q is 0. Okay? So please pay attention to this. Okay, I've seen a lot of people, a lot of you made this mistake. More than maybe like 5, 6 students made this mistake. The idea is that this is not just an application of Lagrange. You need Lagrange, but you need to pay attention about the q. Okay? Yes? P prime, yeah, I said P is prime. Yeah. Yeah. Okay? Are we good here? Okay, so please pay attention. You see where the problem is. I said the cardinality is p to the q. And I put an emphasis that q is strictly bigger than 0. So q is an integer bigger or equal to 1. Lagrange gives you that it's p to the q for some q bigger or equal to 0. I want you to eliminate the fact that q is 0. Okay? If it helps, this question is going to be graded. So like, this is what I'm saying. Okay? Yeah?
Then q is not greater or equal to 0.
No, Lagrange tells you that ZG is p to the q for some q greater or equal to 0. Right?
Okay.
I want you to eliminate the fact that q is 0. Yes, sir?
So if we prove that like q is not 0, then like that's the proof we get.
Yeah, if you prove that q is not 0, then you get that. Okay? So please pay attention. Okay, so this part will be graded, that's why I'm telling you. Okay? Great. Okay. The homework 4 is posted. Homework 5 is posted. Did I post it or not? No? Okay, I'll post it then after. And I'll release the grade of homework 3 as well. Okay, great. Now let's get back to where we were. We were saying let G be a group, of course. And G be a group. The set G to the n as n is in Z, the subgroup, the cyclic subgroup generated by G, right? We call it this, is the minimal subgroup containing G, subgroup of G containing G. So basically, if H is a subgroup of G and G is in H, last time I had G is in G, thanks for the ones who brought this up, then the subgroup generated by G is a subgroup of H. Okay? Now usually this does not mean a strict inclusion. This could be equal. Okay? Okay? Great. I'll let you prove this. That's clear, right? That's clear, right? Yes, sir.
Minimal subgroup just means subgroup is not an algorithm.
Pardon me?
What do you mean by
Minimal subgroup in this sense. If H is a subgroup of G, and G belongs to H, then this subgroup must belong to H. Okay? So if G belongs to a subgroup, right? If G belongs to a subgroup, then the subgroup generated by G must be part of that subgroup. Okay? This is mean the minimal subgroup. This is what minimal is not a really mathematical word here, but if you have H, if G is in H, then the subgroup generated by G is a subgroup of H. Okay? So if H is a group and you have G, then you have all the powers of G in H. That's clear, right? Is that clear? Is that clear why? So if G belongs to H, then G squared belongs to H, and G cubed belongs to H, and G to the 4 belongs to H, and the inverses of these belongs to H, and so that's all. Okay? Great. Now, if G has finite order n, then G, and the subgroup generated by G, is just the identity G squared right? That should be clear because any power, is that clear? Then all the powers must be distributed. Right? I mean, you know. So let K be in Z. Right. K as Q, this is N, well, order of G is N. So Q N plus R, where Q is in Z, and 0 R N. G to the K will be equal to G to the Q N plus R, which is G to the N to the Q and G to the R. Now G to the N is the identity to the Q, G to the R, which is just G to the R. Okay, so G to the K is equal to G to the R. Okay, so you take any power, G to the 1000 say, and say that the order is 5. If the order of G is 5, reduce 1000 modulo 5, you get 0. So G to the 1000 is identity. Right? Is that clear or not? Is that clear? Really? Okay, so great. I mean, let's do that. You know, suppose G has order 5. G to the 101 is equal to what? To G, right? Yeah, you see that? Everybody, do we see that? Right? Write down G to the 101 as G to the 100 times G. This is G to the 5 to 20 times G, which is just G. Okay? So you reduce the power modulo the order, and then you get back a power in this set. Okay? Great. Okay, now the definition of a cyclic group. A group G is said to be cyclic and only if, well, I mean, okay, there exists G in G such that okay? So if a group is can be written, if all the elements of a group can be written as the power of all of one element, then this group is cyclic. Let's give an example. Z plus, of course, is cyclic, right? Yes?
For the example, G has order 5.
Yeah.
So you're saying that the order of n is equal to 5.
N is equal to 5, yeah.
So if n equals 5, how can you have G for a number?
Yeah, you can have, well, you can raise to any power you want, right? You can raise to any power you want, but G to the 101 will be equal to G, right? So G squared, G to the 0, which is the identity, G4, G5, which is the identity, G5 equal identity. What is G6? G, exactly, okay? So basically it cycles back. Okay, so Z plus is cyclic. Why is that? Can you write, yes?
Well, if you put G equals 1.
If I put G equals 1, exactly. So Z is equal to the subgroup generated by 1, right? Remember, here it's addition. So taking the powers of G is really adding the multiples of 1. So 1, 1 plus 1, 1 plus 1 plus 1, 1 plus 1 plus 1 plus 1, and so on. And then you have 0, and then minus 1, and then minus 1, minus 1, then minus 1 plus 1 plus 1, right? You see that? Everybody, do we see that? Are we good here? Do we see that 1 generates Z? Is every element of Z a multiple of 1 or not? That's it. Okay? Since. And it's also equal to minus 1. Is any element in Z a multiple of minus 1? Yeah. Now, is Z equal to, is this true?
No, because you missed one.
Because?
If you missed the odd numbers, you missed
Exactly. This is false because the multiples of 2 are not the entire integer. Right? Is that clear so far? Yeah? Okay. No. Okay. Are we good here? Everybody, is it clear? Please ask. Is this one clear? Right? I mean, you know, when you have, remember, when I'm talking about the addition, G to the n is not really a power. It's just like the operation applied n times. So when I say the addition applied n times means 1. 1 plus 1. 1 plus 1 plus 1. So really these are the multiples of 1. Is any element in Z a multiple of 1? Is any element in Z a multiple of minus 1? Yeah. So Z is cyclic. Okay. What's another cyclic group? What's another cyclic group? R is R cyclic. Okay, so let's see if you, yes sir. Here? Why are these two are equal?
Yeah, like to me it seems like the second one should just be all negative since you're adding -1 and -1.
Yeah, but it says that this is the subgroup generated by minus 1. You're adding the negative 1 and you're putting their inverses as well.
Okay.
Right?
Which is the positive.
Exactly. So really, when I say G to the n, as n is in Z, the negative parts, the G to the minus 1 is the inverse of G. So you put the negatives, minus 1, minus 2, minus 3, minus 4, minus 5, and you add their negative inverses. So 1, 2, 3, 4. Okay? Okay. Is R cyclic? The question is, the answer is no. Okay? Is Q cyclic? Also, okay? Q Q is not cyclic, R is not cyclic. Yes,
How would you prove that a set is not cyclic?
you can see the homework. Okay? Okay. I think I put these two questions. I think I put one of them. But I mean, try to think first about cardinality of a set. A cyclic group must be countable, right? Okay. G squared, G cubed, G to the 4, G to the n, right? This is a countable set. Is R countable? So this is not. I think that's a proof that eliminates R. Now for Q you have to do something else. Yes, sir.
When we said that if G has finite order n, then like you could have like G to the 1, G to the 2,
Yep.
to G to the n.
Yeah.
And if it's like infinite n,
You just have G to the n as n is in Z.
you just like keep going.
You keep going. Exactly. One has infinite order in Z. You just keep going. Exactly. Okay? Now what's another nice cyclic group? Z mod nz, for example. Z modulo nz. With addition modulo n is cyclic. Right? What's an element that generates it? Also 1. Right? Okay? Great. Okay. I'll state an obvious result. Algebraic group. G be a finite group. Should you do one more example of a finite group, of a cyclic group? Let's do that. So let's take U5 for example. The integers modulo 5 that are co-prime with 5. With multiplication. Is this group cyclic? Let's look at what's the order of 1. Here the operation is multiplication modulo 5. So the order of 1 is 1. What's the order of 2?
It's going to be 5.
Okay, what is your, let's look at something. If I want to look at the order of something, so this is a group of, what is the size of this group? What is the size of this group? 4. So what are the possible orders I have? By Lagrange. 1, 2, and 4. So really, let's have a look. So what is 2, well, I'll just, 2 squared, what is 2 squared equal to? 2 squared is equal to 4, which is equal to, well, it's equal to 4, right? And what is 2 to the 4? 16 is equal to 1, right? Okay, so 2 has order 4. Now let's look at 2 cubed. What is 2 cubed? 2 cubed is 8, which is 3. Okay, so I'm good, read. 1 is equal to 2 to the 0. 2 is equal to 2 to the 1. 3 plus 3. 3 is equal to 2 cubed. 4 is equal to 2 squared. Right? Mod 5. So this group is cyclic. So U5 is cyclic. What you need to do is find an element whose powers are all the other elements. 2 is such an element. What is 2 to the 0? It's the identity. What is 2 squared? What is 2 to the 1 is 2. What is 2 squared is 4. What is 2 cubed is 3. So you wrote all the elements of U5 as the power of one element. Okay? Is that clear? So U5. Okay? Great. Let G be a finite group of order n with n elements. Then G is cyclic. If and only if G has an element of order. I mean, this is kind of obvious, right? If you can write G, the entire set G as the powers of some elements, then this element has to be has to have order n, right? Yeah? Is that clear or not? Is that clear? Okay, I mean the proof is left as an exercise. I mean, you know, I'll do one way. Suppose G has an element of order n. Suppose you have an element G of order n. Then the subgroup generated by G, e.g. G squared, G to the n minus 1, is a subset of G. I mean, it's a subgroup, but here really it's a subset of G with n elements. Okay? So the subgroup generated by G has n elements, right? Now, if I have a subset G, so G is a subset of G, and G has n elements, and G has n elements. The subgroup generated by little g has n elements, and the subgroup and big G has n elements. What can I say about these two sets? If you have a subset of size 5 of a set of size 5, what can you say about these two things? Yes? They're equal, right? And G. Okay? And the other way is left as an exercise. Okay? And then G is cyclic, but only if G is an order n. So the other. Okay, great. Now, small note, small definition. If G is a group and G is equal to subgroup generated by G, we say that little g generates G, and that what? Or that G is a generator of G. Okay? This is just a definition. Okay? Great. Let's give an example. Is U8 cyclic? Is U8 cyclic? Let's have a look. So what is U8? It's all the equivalence classes of integers that are co-prime with 8, right? What are they? 1, then 3, then 7, right? Do you mind if I drop the indices, or I can just
I mean, you already did that before.
okay, so I'll just write it this way, right? Okay, I mean I can.
You do it anyway.
Okay. Great, with multiplication modulo 8. Okay? Let's look at the order of 1. What's the order of 1? Now, what are the possible orders here? It's a group of how many elements?
It's
How many elements I have here?
4.
4. Great. What are the possible orders? 1, 2, 4. Of course, what is the only element that has order 1? It's the identity, right? 1. So, order of 1 is 1. Now let's take the order of 3. What is the order of 3? 3 squared, what is 3 squared? 9, which is 1. So the order of 3 is 2. Now what is the order of 5? What is 5 squared? 5 squared is 25. Modulo 8 is 1. So the order of 5 is 1. Sorry, the order of 5 is 2. Right? Now what is the order of 7? 7 squared is, look at 7 as minus 1, right?
Yeah.
7 is minus 1, right? And minus 1 squared is 1. So the order of 7
Is 2.
is 2. So really all the elements that are not the identity have order 2. So is U8 cyclic? Let's look at this theorem. Is U8 cyclic?
No.
No. Okay? Since U8 has size 4, but has no element, sorry about of order 4. Okay? Sorry about that. So since U8 has size 4, but has no element of order 4. Okay? Yes, sir. 7 mod 8 is minus 1. Right? And then you square it. Right? 7 mod 8 is minus 1. Okay? Okay? Square both sides, you get that 7 squared is congruent to minus 1 squared mod 8. Or really, you can take the 7 squared as 49, which is 1 plus 48, which is 1 mod 8. Okay? Okay, great. Is our cyclic groups clear? Is it clear what a cyclic group is? Now of course I'll give you a small proposition. I think it's an easy one. Let G be a cyclic group. Let G be a cyclic group. And G is a bit. Is that clear or not? Is that clear? Everybody, is that clear or should I prove it? Should I prove it? I mean, it should be clear, but prove. So a cyclic group means that I have an element that generates it, right? So since G is cyclic, there exists G and G such that G is equal to a subgroup generated by G. Means that there exists a little G in G such that every element of big G is a power of little g, right? Now, so let X and Y be in G. There exists N1 and 2 in Z such that X is equal G to the N1 and Y is equal G to the N2. Now what is XY? XY is G to the N1 and is G to the N2, which is G to the N1 plus N2. That right here is G to the N2 plus N1. So g to the n2, g to the n1, which is yx. Okay? Is that clear? Everybody? Yeah. Okay, so is S3 a cyclic group? S3, the symmetric group on 3 letters, is it a cyclic group? Is it abelian? Is S3 abelian? The symmetric group on 3 elements, is it abelian or not? No, right? The bijections of 3 or more elements don't commute with each other in general, right? Yes?
Is that an if and only if?
No,
Okay.
no.
So we
Let
can't
G-
prove this.
So let G be a cyclic group, then G is abelian.
So
If
we
G-
know that S3 is not abelian, we cannot say whether or not it's cyclic.
No, a cyclic group must be abelian, right? If a group is not abelian, then it's not cyclic, right? S3, so Sn or n bigger or equal to 3 is not abelian. So it's not cyclic. Okay, let's take GL2R, the group of 2 by 2 invertible matrices. GL2R, the 2 by 2 invertible matrix under multiplication. Is that an abelian group? Invertible matrix under multiplication, is that abelian?
No.
No. So if it's not abelian, hence it's not cyclic. Really, I mean, it's not abelian, so it's not cyclic. Really, finite abelian groups, if you have, really the reason we're doing cyclic groups for is that finite abelian groups, these are big kind of, you have a lot of abelian groups. But the building blocks of finite abelian groups are cyclic groups. It's just that the building blocks of integers are the prime numbers. The building blocks of abelian groups, finite abelian groups, are cyclic groups. Okay? So if you know a bit of cyclic groups, then you might say something about finite abelian groups. That something turns out to be a lot of things. Okay? Great. Okay. Okay, now theorem. Well, in this is a small population. Rob?
Sir, wait.
Yeah.
Can you give us an example of an abelian group that is not cyclic?
Sure. U8. U8, we've seen that U8 is not cyclic, right? And U8 is abelian. Okay? So, but not every abelian group is cyclic. Good point. U8 is abelian. Not cyclic. Okay? See the previous example? We have shown this. Okay? I'll rate it. Rob? Let G be a finite group with n elements. And let G be in G. Okay? Then, it's really related to the previous one. Then, G is equal to the subgroup generated by G if and only if G has order n. Okay? That should be clear, right? So if you pick an element that has order n, let G be a finite group with n elements, and let G be in G, then G is equal to the subgroup generated by G if and only if G has order n. Okay? It's really the same. It's kind of the same argument as before. Okay, is that clear or not? Yeah, that should be clear. If you have a group with n elements, then an element generates it if and only if this element has order n. Yes, sir.
What's different about this proposition and the proposition we just
Oh, before what I said is that then there exists a G with n elements. A G with order n. I said that a group G is cyclic if and only if a group G with n elements is cyclic if and only if there exists a G with order n. So here it's a bit related. I say if you have a finite group with n elements, then it is generated by little g if and only if little g has order n. Okay? It has a lot of statements are not the same, but the proofs are almost identical. Okay? Great. I mean the proof is left as an exercise. You know, obvious facts, I try to leave them as an exercise. It's good to try them. You try them at home. See if, you know, 2 or 3 lines. You can get it. Okay? Example, let's give an example. Let's say U5. What we had U5 is 1, 2, 3, and 4 with multiplication mod 5. Let's write down the order of each element. We have shown before that 2 has order 4. 1 has order 1. Right? We have seen this. So 1 is 2. 2 squared is minus 1. And 2 to the 4 is. Now 3 to the 5, what's the order of 3 to the 5? As order. So what is 3 to the 1 is 3. What is 3 squared? Is equal to 1, right? 3 squared mod 5 is equal, no, what am I saying? What am I saying? 3 squared mod 1 is minus 1, and 3 to the 4 is 1. So 3 to the 5 has order 4. Now 4 mod 5 has order 2. 4 is 4, and 4 squared is 16, or 4 is minus 1, right? 4 is minus 1, so 4 squared is minus 1 squared, which is 1. Okay, now what are the elements that generate, so is U5 cyclic first of all?
Yes.
Does it have, it's a group with 4 elements with an element of order 4, right? Now, what are the elements that generate U5? Exactly. You look at the elements of order 4, and these are the elements that generate U5. Okay? Right? I mean, think about it a bit. If you have 3, so how many distinct powers of 3 you have? You have 4 distinct powers of 3. Right? So the distinct powers of 3 must be U5. Right? Is that clear? Is that clear? Great. So U5 is what? U5 is equal to 5. But it's different. Okay. Now, okay, so far so good. It's a bit fast, but these are just simple calculations. Okay? What time is it? Maybe we can do another example.
It's 11:14.
Oh, so I'll just do some theory first, I guess. Well, I mean, you know, let's. Yeah, okay, let's do a theorem first. Okay, now Lagrange's theorem states that if you have a group with n elements, then any subgroup of the group must have number of elements dividing n, right? So Lagrange's theorem states Lagrange's theorem, if H is a subgroup of G and G has n elements, then H divides n. Right? Now for cyclic groups, it turns out that the converse is also true. So for cyclic groups, you do have, for let G be a cyclic group, theorem. Let G be a cyclic group with n elements. And let D divide n. And G has a sub, let's see if I could. Usually this is not in the book, but has a unique subgroup. Okay? With the elements. Okay? And then it's so nice that it tells you what the generator is. So, and this is a long theorem, I guess. But let's include if G is equal to G, then G to the n over D is, well, you know what, let's erase it, we'll see this in the proof, okay? We'll see this in the proof. We'll see this in the proof, okay? Great. Again, these are stuff we have seen, and we're just applying the results we have seen to this. Proof. Let G be equal to G. That's right, properly. Let G be in G be a generator of the cyclic group. So basically, let G be an element of G of order n, basically, right? So G has order n. Now, how do I find an element of order D? So let's look at Z mod 4Z, for example. Can you find an element of order 2? Can you find an element that you add twice and you get 0? 2, right? So now in Z mod 6Z, can you find an element of order 2 in Z mod 6Z? You find an element that you add twice? 3. In Z mod 8Z, can you find an element that you add twice and you get 0? 4. 4 plus 4. Great. So if I want to find an element of order 2, I take 8 over 2. Right? Now in Z mod 10Z, can you find an element of order 5? You add it 5 times, the minimal number of times that you add is 5, and you get 0. In Z mod 10Z. Okay. You see that? If you add 2 5 times, you get 0. And if you add 2 less than 5 times, you will never get 0. You see that? Z mod 12Z, can you find an element of order 4 in Z mod 12Z? Z mod 12Z, an element of order 4? An element of order 4 in Z mod 12Z? 3, right? An element of order 6 in Z mod 12Z? 2, right? Very good. So the idea here is the same. G has order n. Then G to the n over D has order. Notice that n over D is an integer, right? N over D. And if D divides, let D divide n, and D is strictly positive. D is an n as well, right? But I have a negative number here. N over D is n. Then g to the n over d has order. You've seen the formula for this. It's the order of g, divided by the GCD of the order of g and n over d, which is just n over GCD n and n over d. Now n over d divides n. So really the GCD of n and n over d is n over d. Right? So g to the n over d has order d. And hence the subgroup generated by g to the n over d has the elements. Okay? Are we good? Yes? Great. Now I need to prove that this is the unique subgroup of order d. It's not very much difficult. It's not more difficult. But let's see. Okay? Let H be a subgroup of G with D elements. And let Y be in H. What I really need to show, we need to show that Y belongs to G. That's what I need to show. Right? Great. Now, how do you prove that? So, first of all, by Lagrange's theorem, you have many consequences, but by Lagrange's theorem, we know that Y to the number of elements of H is equal to the identity in G, right? Lagrange's theorem that the element raised to the power of the group is the identity, right? Because the order of Y divides the order of H, right? And so when you raise Y to the power 8 to the number of H elements, you get EG. So Y to the D is equal to EG. Right? Are we good here? We remember this result? If you have a finite group G, then the order of little g divides the number of elements of G, and hence G to the number of elements of G is the identity. Okay? Please stay with me 2 more minutes, so that just I finish it. So Y to the D is EG, hence there exists. Now, since G is cyclic, there exists K in n, K in, there exists K, let's say 0, 1, up to n minus 1, such that Y is equal to G to the K. So Y to the D is equal to G to the KD, which is equal, well, this is equal to the identity. So G to the KD is equal to the identity. Right? Now if I have G to some power equal to the identity, this means that the order, this implies that the order of G, hence order of G, divides KD. So N divides KD. Sorry about that, just finished it. What time is it? 25. Just 1 more minute, and then I'll finish it. I just don't want to start it again. So N divides KD. I mean, it's an argument we've seen many times. So Qn is equal to KD, right? Agree? For some q in n. K is positive, D is positive, N is positive. Great. Now let me divide both sides by D. And I still remain in integers, right? Is equal to K. N over D belongs to N, since D divides N. And these are all positive numbers, strictly positive numbers. So really I have that K, that N over D divides K. Right? So Y is equal to dk is equal to G to the N over D times Q, which implies that Y is equal to G to the N over D to the power Q. So really Y is a power of G to the N over D. So Y belongs to the subgroup generated by G to the N over D, and hence H is a subset or a subgroup, say, of G to the N over D. Okay? Now this has D elements by assumption. And this has D elements because G to the N over D has order D. H has D elements by assumption. By assumption. And G to the N over D has D elements since G to the N over D has order D. Okay? Sorry about that. Sorry. Okay? Great. Now, this has D elements and this has D elements. What can I say about these? Then H is equal G to the N over D. Yeah, one more theorem. One more. No. Okay? Sorry, I just wanted to finish it. Now,